Perfect timing. Thanks, Bob Marley. All right. Again, in lesson 21 is when we're pulling all of our info together and being able to use it, rewrite things in different ways so we can solve unknown values, make some calculations, and see what we're doing. So we know we're anticipating some fractional equations. And we mentioned yesterday we can check if we have the same numerator or denominator. That would help speed us along. Or if we can find a pattern that would help us solve from one denominator or numerator to the other, that could make it easier. And if all else fails, cross multiply. Remember, you're doing top to bottom on opposing fractions. We need an equal sign in between so we can take that equals and kind of cross multiply from there like that. So I always think about that, taking that equal sign and cross multiplying. So we're going to talk about boating for a little bit, which is kind of cool, and see how we can start to calculate some information. Noah likes to go for boat rides along the river with his family. In still water, so if they're in like a lake or something, the boat can go 8 kilometers per hour. So there's like what the motor is capable of going. But in the river, it's kind of a different case. So if this is them on their boat can go this direction. It can push them forward at 8 kilometers per hour. But in a river, you have this current that's pushing against you or pushing with you. All right, so in here, let's say that the river is flowing that way. So in the river, it takes them the same amount of time to go upstream 5 kilometers as it does to travel downstream 10 kilometers. Upstream 5 kilometers, downstream 10 kilometers. So it sounds like what I'm hearing is that this is a problem dealing with distance, rate, and time. I have distances of 5 and 10 kilometers. I have a rate of 8 kilometers per hour, and they're telling me that it takes the same amount of time. So let's remember our formula that distance equals rate times time. It's asking us for an expression for the time it takes. So I want to get time by itself on one side of my equation. So to do that up here in our equation, in our formula, to get time by itself, I would need to divide both sides by rate so that time is then isolated. So if I'm writing an expression for time, time equals distance divided by rate. I feel like this is back to the idea of Kieran, who was going for a bike ride with his aunt. So we're bringing that info back here. So we need to write an expression for traveling upstream and a separate expression for the time it takes for downstream. All right, let's write these two expressions and we'll see what we have here. Let's start with our upstream equation. Upstream, t, time, equals, let's see, the distance that they're going upstream tells us that right there. We've got 5 kilometers going upstream. So there's the distance that they are able to go. 5 kilometers distance. And we need to think about the rate that they are traveling. Now, if they are going upstream, it means that they are fighting the current. So while the boat is trying to go 8 kilometers per hour, that's the start of our rate, 8, because the boat is trying to go 8 kilometers per hour in this direction. We have the current that is pushing against them and slowing them down. So the current pushing this way is going to slow their rate. That means we're going to subtract from that 8. We don't know what the speed of the river is, what that current is, but it tells us to use R to represent the speed of the current. So it makes sense for us to use subtraction there because the boat is trying to push this direction, the current is pushing against them and slowing them down, so we're going to have a slower rate than 8 kilometers per hour. So we have accomplished our mission. We wrote an expression for the time it takes to travel 5 kilometers upstream. We need to do the same thing for downstream. Downstream is going to take a certain amount of time. What's the distance that they're able to go downstream? Nice, perfect. Right on, thanks for that. 10 kilometers. All right, so 10 kilometers downstream. And with our same kind of model that we're looking at with our rate, we have the boat that can go 8 kilometers per hour. But this time, the boat is going downstream. It's going with the current. So imagine this boat is going this direction with the current of the water. They're heading downstream. That means they've got their boat going 8 kilometers per hour, and the current is pushing them even faster. So instead of subtracting the current rate, we're going to add to it because the boat can go a certain speed and then the current is pushing on it. I see Ben's nodding and he's like, he knows all about sailboats and using all this kind of stuff. So you're like, man, this makes perfect sense. So not only is the boat motor pushing the boat in one direction, now the current is also pushing it faster. That's why they can go farther in the same amount of time, because the current is helping them to go faster. We have accomplished our 2 missions. It asked us to write 2 equations, so there's my answer. I'm going to box that in because I'm going to use that in our next question. Question number 2 on the top of the next page asks us to use our expressions to calculate the speed of the river. It's like, well, now that we have these 2 R's going on, could we figure out how fast the river's going? So a key word or a key part of our problem sets us up for success with this. That key part is that it takes them the same amount of time. So these 2 t values have to be equal to each other. If it takes both directions equal time, we can set these 2 equations equal to each other, right? If this one equals t and t also equals this one, then we can set these 2 equations equal to each other and see how we're going to solve that. Let's write that up here with our 2 expressions equal to each other. 5 divided by 8 minus r equals 10 divided by 8 plus r. So our time upstream equals the time it takes downstream. Now, if I'm looking for how I could go about solving these, there's a couple different ways we could go about it, and I'm going to look at our ideas from yesterday to see one way that we could go about doing this. Are both of our numerators the same, or are both of our denominators the same? No, we got some differences here. 5 is not the same as 10. 8 minus r is not the same as 8 plus r. So I can't, nothing's the same. There is a pattern, a multiplier, from one numerator to the next. Do you see that difference from 5 to 10? 5 times 2 equals 10. So 8 minus r times 2 has to equal 8 plus r. So finding a pattern in our numerators means the same pattern has to happen with our denominators. So 2 times 8 minus r equals 8 plus r. I only have one variable, and so we're working step by step in Algebra 1 like we would have to solve a problem in one variable. Let's ask you guys what you would do first. So I'm going to see, let's hear from a couple people. A and B, would you tell us what you would do first in this as you were starting to solve this equation? Aiden, do you know what you would do first? What step would you take?
Sorry about that. There was a lot of noise a little second ago.
That's okay.
Can you ask the question again?
Sure, yeah, you bet. If you were looking at this equation here and knew what we're looking at for our two sides, what would be a step that you would take to solve this? The next step you would take?
I would probably subtract 2 from both sides.
All right.
Divide 2, I mean.
Gotcha. All right. So that is one way that we could think about. Right now it's multiplying by 2. And so we could do the opposite operation and we could divide by 2. Let's ask around and let's see if someone else has a different idea of what they would do. Emma, do you have an idea of what you would do too? I want to see if you have a different way. Yeah. Or if it's the same way. All right, so you see that multiplying by 2 and you would think that we would divide. Let's give it a shot. So if I divide both sides by 2, we would have to make sure that we divide every single term, so each thing that's separated by division and subtraction. That is a very valid step to do. There are other steps that we could have taken, but this is a great one to go with. Just remember that you are dividing every single one by 2. It's going to actually create a fraction that we would need to solve, but that's okay. We can do that too. 8 minus r is all that we would have left on the left side of this equal sign. Nice. And Ollie's saying 8 divided by 2 is 4 plus r over 2. Or I can rewrite this. If I'm taking r and dividing it by 2, I'm going to actually rewrite this as 1/2 r. I'm taking r and dividing it by 2, so I'm taking half of r. All right. 8 and H, where would you go from here if you were looking at something like this? What would you start to think about for algebra, how we would solve?
I'm honestly not too sure.
Okay. Give it a guess. What would, I mean, if this was something that was just set in front of you and was like part of a quiz or a test or something.
Would you do something with the half R or something with the R's?
All right, nice. I like this. Doing something with the R's. Right now I have R's on two different sides of my equal sign. We want to get all of our R's on one side together. So that's a nice way to think about it. I would add this R to both sides. Right now it's subtracting. And I like working with positive numbers. I think a lot of you guys like working with positive numbers as well. So let's add an R to both sides. We're going to add one R. So 8 minus R plus R. We did that so that those R's would cancel each other out. On the left side, all we have left is 8 equals. I'm not adding anything to the 4, so I'm going to just keep that 4 right where it is. And I have half an R, and I'm adding one more full R. So we could write that as 1.5 R, but I'm going to write it as an improper fraction. Because, or you know what, why don't we do it as a decimal? I think people like decimals a little better than fractions. Nice. So we'd have 1.5 R. We have an R and a half. We have 1.5 R. Good idea, Aiden. Does that make sense how we would just then, I like your ideas that you're like, well, we've got a couple R's. Let's get them on the same side together. All right. Ollie, what would you do from here?
Okay.
Yeah.
I'll subtract the 4.
All right. Ollie is saying, just like we had R's on two different sides, we have constants on two different sides. Let's move that 4 over with the 8. So we've got our R's on one side and our constants on the other side of the equal sign. Let's subtract 4 from both sides of our equal sign.
And you have 4 equals 1.5.
Nice. 4 equals 1.5 R. And now our very last step of our equation. If they're multiplying, our opposite operation is to divide. We're going to divide both sides by 1.5. And this I would use a calculator for. I could do it in if I had
2.6.
lots of time, but I also have this wonderful calculator. Might as well use it. Ooh, make sure I put that in right. So 4 divided by 1.5 gives us a current of this river of 2.6 repeating. So this river's current is going about 2.7 kilometers per hour. That's not, I don't know, that's a decently moving river. So we can set up rational expressions and we can find a pattern in order to solve them. If finding that pattern was maybe something that you were like, I don't know if I would have done that. Will you follow with me while we do this just a different way? We'll do it right up on top here. A second method that we could have used to solve it. It's always good to have options. If we just cross multiplied, we would have come up very much with the same kind of idea pretty early. So cross multiplying 5 times 8 plus R.
So 40 plus 5.
All right, nice. So hang on to that thought because I'm going to come to you with that. And then cross multiplying the other diagonal, we would have 10 times 8 minus R. Now, here we went and we did some division first, and that's a valid way to do it. Ollie, what was your suggestion? How would you take it from here?
You put 5 into parentheses.
All right.
That's like as a distributor.
Yeah, nice. So Ollie is remembering the distributive property that we could multiply that 5 with whatever's in there.
So 40 plus 5.
Nice. So 40 plus 5r.
And then 8 minus 10.
Nice. 80 minus 10r. So this is another way we could have gone about it. And that's actually another step we could have taken here is we could have distributed that 2 into the parentheses. We would have come up with the same answer, just a different roundabout way of getting there. So I want to bring you back to this idea that we might be cross-multiplying and we might need to use a grid to multiply. That's why we learned that grid and perfected that grid use first, because we might have polynomials times polynomials. All right, from here I'm going to go with Aiden's method that I like so much of getting the r's on one side and the numbers on the other side. So I would add 10r because I like having more positives. So over on this side, we would have 15r. In the same step, I'm going to also combine our constants. So I would subtract 40 from both sides.
Equals 40.
That way, our 40s here would cancel out, our 10s here would cancel out. And 80 minus 40 is where I'm getting that 40 from.
Divide by 15, right?
There we go. Then we just divide by 15. And it should be the same number. I know that it is already because we are smart mathematicians and we're getting the exact same answer. So it's good to have a model of both ways of doing the same problem here so that you can see that either way is going to work. If we're going to try to find this pattern way, we can solve through. If you like the cross-multiplying way, we can cross-multiply. Let's try a practice problem together. I know there's a rational resistance. This gets really wordy. Ugh.
Let's go.
Yeah. It is definitely a time where you might use rational expressions. But let's tackle a practice problem or two. And then over the weekend, I'll ask you to finish up anything in lesson 21 practice problems that we don't get to. All right. So it's good to have a couple more models and some practices together. I'm going to call on you guys too a lot to be giving me some input about what you would do or how you would start to solve these. So please be following along with us and be ready to share your idea of what step you might take as we're solving through. Alrighty, so I see we have on one side a linear expression and on the other side we have a rational expression. Right now, this one as a linear expression, you might be thinking, oh, well, that's not a fraction, so I can't cross multiply, or that's not a fraction, so I don't know what to do with this here. Nice. So Ollie's got a great idea that any number that we have or any side that isn't already a fraction, we can make it be a fraction just by dividing it by 1. And then we can go through how we might. I noticed that none of the numerators are the same, the denominators are not the same. So for this one, I would go right into cross multiplying. So we're going to cross multiply x minus 1 times x plus 2 equals our cross multiplication the other direction. It's multiplying by 1, so it's really not changing any of our values up here in the numerator. It would just be equal to x squared minus 4x plus 3. So I've multiplied crosswise x minus 1 times x plus 2 equals my cross multiplication in this direction. 1 times x squared minus 4x plus 3. Oh, I see Ollie's already hard at work multiplying together. All right. If we've got multiplication over here, we already have something in quadratic over here. Yep, let's go for that multiplication. There's nothing that I can cancel out or that would make sense to get rid of. So I would keep using the grid for this. So I'm going to set up my little grid over here. If you prefer distributive property, go ahead and use distributive. Just make sure you're multiplying everything by everything else. So I'm multiplying x minus 1 times x plus 2. X times x is x squared. X times a negative 1 is a negative 1x. X times a positive 2 is a positive 2x. And positive 2 times a negative 1 is a negative 2. When I combine like terms, I've got some x's there in the middle. So I have an x squared, 2 positive x's, 1 negative x, combining and adding those together. Please remember at this point you're adding. There's a plus sign right there in the grid that helps us remember that. 2x plus negative 1x is a positive 1x, and then a minus 2. All right, so we have rewritten this. Nothing changed on the right side of my equation, but I rewrote this to put it into standard form. Alize, where would you go from here? What would you do as your next step?
I feel like I would cancel out the x's.
All right, nice. As we're starting to think about these things, we want to start trying to bring some things together. So we're going to, I like to, and I think this is where you're going, this idea about what we can cancel out, what we can start to bring over together. All right. Right now, everything on either side is actually just adding and subtracting different terms. So if I have an x squared on both sides, it's adding and subtracting. So I would subtract that x squared on both sides. So remember, it's using opposite operations. Right now, these three terms are adding and subtracting each other. So we want to use subtractions on both. What I love about this is that it actually cancels out both of them. On both sides, by subtracting an x squared from both sides, I've canceled out both. One x minus 2 equals negative 4x plus 3.
Added 4x to both sides.
Nice. All right. Let's keep on going with this idea that Alize was talking about, that Aiden suggested, and that Ollie is saying now. Let's keep on moving everything to one side together, or we'll move all of our x's from one side to the other. Let's add 4x to both sides to keep it a positive number. Nice. And Ollie's saying we can even do it in the same step. If you can think, if you're working that far ahead, I'm going to keep it as 2 separate steps because I like to just keep myself in some nice order here. Negative 4x plus 4x cancels out. On the left side, we have 5 x's. And then Ollie was saying, well, if we get all of our x's on one side and we don't have an x squared or anything like that, let's get all of our constants on the other side. Five x equals 5. Oh, cool. Awesome. 5 times something equals 5. That something has to be 1. Just curious what this looks like on Desmos. We haven't used Desmos for a little bit. I'm curious what this looks like on a Desmos if I had these two things equal to each other. So I'm just going to have my x minus 1 as my first equation. And I'm going to put my other equation. Now my whole numerator I'm going to put into in parentheses, so it all stays up on top. X squared minus 4x plus 3. All of that divided by, and as soon as I hit that division, you see how Desmos nicely makes it the fraction I'm looking for. X plus 2. Oop, not equals. Plus 2. So I have my 2 graphs, and it makes sense that one of them has this curve going on because there's an asymptote happening. And I can see where the 2 of them are crossing each other. Look at them crossing right there when x equals 1. So I can see that my Desmos also confirms that. Will you sketch a little graph in your workbook that looks like this Desmos graph so we can see that these two, and Desmos is a great way for us to verify our assumptions about where we think these things are going to cross each other. That's it. So I gave just a little sketch there, kind of showing our 2 graphs and how they cross.
So we're going to do the practice on Monday?
Monday, yep. So please look at practice problem set for the rest of 21. Just a couple more problems, and some of them are review from earlier in our unit. And we will check through our practices on Monday when we're back here together. All right? Thank you, friends. I appreciate your help. Great effort, great work together, great suggestions for how we would go about solving these.
For 2, I got 0.41.